Okay, in this presentation we're going to look at how to compute the correlation coefficient. Now, just specifically so you get more comfortable with the terminology, we're going to compute Pearson R, Pearson's R, or Pearson R, Pearson's. Essentially, just look out for this word here, Pearson. This is a very famous statistician who developed a lot of tests that you would see in undergraduate statistics, tests and procedures and so forth. R is the estimate for the population correlation value, which is rho. Okay, so essentially, let's actually write that in because that's important. R is an estimate for rho. Okay, Greek letter, which is essentially the true correlation or the correlation, the population value for the correlation. Okay, anyway, what we're going to do here is work on the basis of these sums of squares identities. Okay, so there's a couple of different variants of calculating the Pearson R. They actually all fundamentally the same, but they actually present it a little bit differently. So what we have here are sums of squares identities. Okay, so we have SXX, SYY, and SXY. Okay, sums of squares identities. You don't really need to know what these are, to be honest with you. You might be given them in somewhere in your exam paper. Sometimes you might have to calculate them all out from scratch. So I'll just show you what one of them is here. This is SXX, and this is essentially for each value in a data set X, subtract the mean, square it, and add all the terms up. Okay, so this is actually how we would compute variance, okay, of X. Okay, essentially what we do there just to compute variance is just divide by n minus 1, where n is the sample size. So it's essentially a component in that calculation. So that's all we're really doing here. And when you're given sums of squares identities, you're just given sort of the some of the calculations done for you in advance, and you just have to finish them off. Okay, so that's essentially what sums of squares identities are. Okay, when in the context of calculating correlation coefficients and so on. So here's a little example here. Suppose SXY equals 79, SXX is 125, and SYY is equal to 80. Compute the correlation coefficient, okay, Pearson R. Okay, now so let's have a crack at that. Oops, I went too far there. Let's go back here. There we go. So essentially what we have to do here, let's just sort of like remind ourselves what the formula is here, and I have it written at the start. So essentially what we have here is SXY divided by SXX, the square root of SXX times SYY. Okay? So there we have them there. And just before I sort of continue on, I'll actually just sort of state this is related to the covariance of X and Y. This is related to the variance of X, and this is related to the variance of Y. Okay, so if you see formulas, a different set of formulas that mention covariance and the variances, covariance of X and Y, and variances of X and the variance of Y, or the standard deviation of X and Y, that's essentially, fundamentally, they're all the same thing. Okay, anyway, let's just go back to work here. So here we have it there. This is, let's just write it again, SXY over the square root of SXX times SYY. Okay. And so let's calculate that out. So 79, that's left alone. Okay. So this is the square root of 125 times 80. That's actually 10,000. Okay, just be careful with those numbers there. Actually, the square root of 10,000 is actually just 100. 79 over 100. So it turns out to be a nice simple number here, 0.79. Okay, so just remember, it's sort of good to interpret a number like this. Okay, so I'm going to sort of interpret this as strong positive linear relationship. Okay, now what should happen there is that you should also have a scatter plot. Okay, and you have to check, is the relationship linear? Because sometimes you might be asked that, is the relationship actually linear at all? Because you can calculate a correlation coefficient in the for data where there clearly isn't a linear relationship. So it's still a calculation you can do, just doesn't make sense. So essentially, what you should do there is just check the scatter plot, just to sort of check, is the relationship fairly linear. That's just an important step. If it's the scatter plot's not given, just making a sort of this is assuming that the relationship is linear. Okay, something like that there. Okay, so just check somewhere, is linearity a good assumption, or just make a statement, this is assuming linearity is relevant here. Okay, now it's actually something I'm going to just go do here, just before we finish up. This is a short discussion here, but essentially, how do we interpret them all? Okay, so what I'm going to do here is just sort of come up with my own sort of little sort of thresholds. 0.9 to 1.00. Okay, that I would say that is very strong positive. Okay, 0.7 to 0.9, just strong without being very strong. So strong positive. 0.5 to 0.7, I'll say mildly strong. That's not how you spell mild. Whoops. So M-I-L-D, mildly strong positive. I'll just make some space here. 0.3 to 0.5, weak positive. Okay. Now, what do we do here? Or actually, I'll make it a little bit sort of narrow, wider, 0.2 to 0.5. Again, these thresholds are very arbitrary. Minus 0.2 to 0.2, sort of essentially no discernible relationship, or no linear relationship. No discernible linear relationship. Okay. Then we just sort of do go in reverse, but now we're on the negative side, so I'll just go to a new page here. So minus 0.5 to minus 0.2, weak negative. Minus 0.7 to minus 0.5, mild. Mildly negative. Okay. Minus 0.7, 0.9. Whoops, 0.9 to 0.7. Stop acting up. Weak. No, strong negative. And then finally, minus 1.00 to minus 0.9, very strong negative. Okay, so that's how we might interpret them. Now, that's only sort of rough guidelines there. I mean, it's not there's no sort of set rules about how to interpret these correlation coefficients. But it's just a sort of, you know, you might be asked to put some sort of interpretation on your answer. So on this answer here, just sort of interpret it a bit is useful. Okay, that's it. How did we do? 9 minutes. That's a long one.